Welcome to the talk about the paper with the title Event-Based Data-Centric Semantics for Consistent Data Management in Microservices. My name is Tilman Zuckmantel. And when we say microservices, let's first look at what exactly we understand when we say microservices. So in our example here, we have three microservices, three components. One is responsible for managing orders, another one is responsible for managing customers, and we have a third one that is responsible for managing payments. And what is important is that each of these components, it has an individual database. And also, very important, the communication is purely event-based and also therefore asynchronous. So the agenda for this talk is we have two examples that we will take a look at, and both of them we will look at a motivating example and also a vision. And then next we will see how we can combine our two visions and also go into a conclusion. So for a motivating example, let's look at the following unsafe interleaving. Imagine that we have two events that arrive at the two microservices orders and customers in about the same time. So one event is called place order, and it will trigger a place order function inside the microservice, which will then try to place an order inside the database. The other one will try to delete a customer. And now in our scenario, the customer's microservice, it starts by contacting the orders microservice to see if there are any existing orders for the customer that we want to delete. So the orders microservice will reply and it will say, okay, no, there are no orders at the moment for this customer. And it will start, the customer's microservice will then save that locally. Next, the customer's microservice will contact the payments to see if there are any ongoing payments that are not processed. Also, in our case here, it is the case that the payments microservice needs a bit of time to process this request. Maybe something else is processing at the moment, and in the meantime, the place orders function starts, and it starts by contacting the customer's microservice to see if the customer that we want to place the order for actually still exists. And here we get an answer, so yes, indeed, at the moment, the customer does still exist in the database, so we save that also locally. And then the payments microservice proceeds the request and says, no, there are no payments for our customer. So now we are in a state where we have locally saved that the customer exists and that there are no orders and no payments. And therefore, we have the problem that the orders microservice thinks, okay, the customer exists, I'm going to put a new order in the database, while the customer's microservice will delete the customer from the database. And that, of course, is a globally inconsistent state. And the cause for this is an uncontrolled data race. So we have, in the one side, read the customer from the database, and on the other side, another transaction or another function has deleted that customer. That should not occur. Okay, so what can be done? So what is possible to do? On the one side, what is popular is to implement own orchestration methods. And the plus side here is that we get ultimate freedom. So if we implement our own orchestration methods, of course, we get the maximum freedom. But however, we have no guarantees of what is happening inside the architecture. Then we could also use something like a traditional protocol like 2PC. And 2PC typically grants atomicity, but it introduces a strong coupling between the components and also blocks the processes. Last, what got quite common quite popular in the microservice community is the Saga pattern, and that is a method which is non-blocking, and it also provides atomicity, but it has no isolation guarantees. And what are we ultimately looking for? So we are looking for a process, for a methodology that gives us atomicity, it provides isolation, it is non-blocking, and it preserves the modularity of the microservices. So let's look at what we envision to do. And maybe as a motivation here, just look at when the orders microservice contacts the payments microservice by sending an event, and the payments microservice will reply with an event, then a function gets triggered in the payment microservice which does something, right? But what this function is doing inside the payments microservice, it is not observable for the orders microservice. So this is a kind of the business function that gets triggered is not observable. It's a black box for the orders microservice. And what we are thinking to do is that we introduce specifications. So we publish specifications of our functions, semantic representations of the functions inside a central coordinator to then observe the functions. And the question really is, how can such a specification look like? And what we are taking for a semantic model is something that is called an interface automaton. And this interface automaton, it is an automaton, a finite state machine, but it is expressing the sending and receiving of messages. And that is quite what we want also for expressing microservice functions. And also a big advantage is that these automaton are not input enabled, meaning that we do not need to have a transition for each element from the input alphabet in the automaton. Furthermore, there is a composition operation. So if you have two interface automaton, then you can compose them to get a composed automaton. And this will get much more clear if we now take an example. So let's look at the place order event that comes in here and then triggers the business function. And let's model that business function. So place order is starting, and in the automaton, we would model this by stating a receiving event. So we are receiving a place order event, and the receiving is modeled here by the question mark. And we also get an ID and we get an order. Next, we would get we contact the customer's microservice and we will get an answer, and we model this again by sending an event. So here the exists customer event is sent, and we model this by an exclamation mark, and then we receive an answer again with a question mark. And next we implement the if branch that we would have here. So depending on the answer that we get, we will either go in the one path or we will go in the other path. And if it turns out that the customer exists, we will directly model here the data operation on the database inside the automaton. And that is the key part here. So we make the database operation observable inside of the automaton. Okay, last we conclude by sending success or fail on transaction finish. And if we now take the place order function, the delete customer function, the exists customer function from the microservices and compose them together, we get a semantic representation of the interleaving. And let's look, if we put that now, this semantic representation into the coordinator, let's look how this can improve the example that we had before. So right here you see an excerpt from the composition, and let's say we know that the read operation is from transaction 1 and the delete operation is in from transaction 2, and we know that we are in the state that is marked here with the bars. And next, the payment exists event would come in with a response of false. And we also know, because we have a local storage of O is false and P is false, and we can look ahead from our state, we know that what would happen is that if we take this path, we would indeed delete the customer from the database while before reading it. So we would violate serializability. And that is the core part of this idea. So, however, it is not everything that we can do. Furthermore, it is possible to actually proactively only take paths that don't end up in a deadlock, because we always can analyze which kind of path are safe to execute. And then we can also semantically collect semantic information if we have to abort a transaction, because we know the semantic step that we have done in the past. So for example, if we would have done an update to the customer's database, we would be able on the board to send that to the customer to make sure that this gets reverted in the database. Okay, our second example is a little bit different, because here we have something that spans more than one transaction. So for example, here it says, never should it be possible to get a reimbursement before completed payment. And as I just said, that is no longer within the transaction lifetime and therefore not possible to use our model that we had before. And what we envision here is if we think of a stream of payment success and reimbursement events, we want to use something that is called metric first order temporal logic. And a formula for stating this would look like this, and we are going to get through it step by step. So this first thing here, it means it always holds that for all customer IDs, if there is a reimbursement, then that implies that in the past there has been a successful payment. And these formulas are actually efficiently monitorable, and that goes back to a paper by Bazin and al. So it is quite a nice way of monitoring these security policies. Together, combining the two elements, we get a centralized coordinator which has both things. So it has the interleaved transaction semantics and it has the causal consistency monitors. And the events would now flow not anymore directly between the microservices, but the events that are critical, so that are involved in critical business functions, they would flow through this coordinator, and our tools will make sure that the interleaving stays consistent. So on the left side, we have interleaved transactions, and that guarantees, so that ensures transactional guarantees, while on the right side, we have causal consistency. We have causal consistency monitors to ensure causal consistency. And to conclude, what is new in our approach? So we introduce formal semantics for microservice functions for transactional guarantees. And further, we introduce a coordinator with a local storage of the transaction state to help guaranteeing the transactional guarantees. And last, we ensure causal consistency by introducing causality constraints by using metric first order temporal logic. So what are the limitations here? So first of all, scalability, of course, is an issue because we don't know yet exactly how we will scale this. We have the idea of making it as a stream processor, but right now it is a limitation. And also it needs to be sure what is exactly the effort for the application developer, and the unintuitive event constraint modeling needs to be improved. And that can be done by using, for example, DCR graphs for graphical interfaces. So thank you all, and let's discuss.